Hey, Jack! Where are you? What you doing over there?
Oh, well, actually, I was just kind of experimenting with uniform circular motion.
Oh, really? Have you ever thought about planetary motion?
You know what? I actually have. I was actually just thinking about what the speed of the Earth was.
What do you think would happen if you increase the radius?
Well, I mean, we got strings here, and we got a couple of ping pong balls. Why don't we just go outside and demonstrate and try it out?
Let's go.
All right.
Jack will be representing Sun 1. The ping pong ball is Earth number 1 with a radius of 20 centimeters. Mitch Sauer will be representing Sun 2, and his ping pong ball is Earth 2 with a radius of 40 centimeters.
2, 3, 4, 5, 6, 7,
As you can see,
8,
both are
9,
going the same
10,
revolutions per
11,
minute,
12,
but
13,
Mitch's ball is going
14,
faster
15,
because it has a longer radius.
19, 20. Planetary motion is based on Kepler's 3 laws. For our project, we focused on his first and his third laws. Kepler's first law states that planets follow elliptical orbits with the sun at one focus of the ellipse. Kepler's third law gives us the equation t, or the period, which equals the time it takes for the planet to complete one orbit, equals a constant times r to the 3 halves. So we asked the question, how fast is the Earth going around the sun if uniform circular motion is assumed? We have to assume uniform circular motion because that takes care of Kepler's first law of elliptical orbits, which we do not consider in this project. For this, we can set the centripetal force equal to the force of universal gravitation. This is because the force of gravity between the Earth and the sun provides the centripetal force. Using Kepler's third law, we can find the mass of the sun. We use the equation stated earlier with a constant of 2 pi over the square root of the Cavendish constant times the mass of the sun, and then we multiply that by r to the 3 halves. Solving for the mass of the sun, we get 4 pi squared r cubed over gt squared. Now, to find the t, we have to convert years to seconds. So by doing those calculations, we get that t is equal to 3.16 times 10 to the 7 seconds. Now plugging that back into the mass of the sun equation, we get 4 pi squared times 1.50 times 10 to the 11th, which is the average distance from the Earth to the sun, and that's cubed, over the Cavendish constant of 6.67 times 10 to the negative 11th times 3.16 times 10 to the 7th. That comes out to 2.00 times 10 to the 30th kilograms, which is the mass of the sun. Now going back to the equation we stated earlier, where the centripetal force is equal to the force of universal gravitation, we set the mass of the Earth times the speed over the radius is equal to g times the mass of the Earth times the mass of the sun over the radius squared. Now the mass of the Earth cancels out, as well as the radius on the left-hand side, so we're left with v squared is equal to g times the mass of the sun over the radius. The speed we solved for as the square root of 6.67 times 10 to the negative 11th times 2.00 times 10 to the 30th over 1.50 times 10 to the 11th. This comes out to about 30,000 meters per second, or 3.00 times 10 to the 4th meters per second. Next we ask the question, how fast will the Earth be going if we double the radius? So if we double the radius and assume the same period, we see how fast the Earth moves if it had 2 times the radius, but it still took 1 year to circle the sun. This is purely theoretical because Kepler's third law states that the period increases as its average distance from the sun increases. However, we like our 12 months, so we assume that the t is still the same at 3.16 times 10 to the 7 seconds. This keeps the mass of the sun at 2.00 times 10 to the 30th kilograms. So we take a new radius of 1.50 times 10 to the 11th meters, and we double that, so we get 3.00 times 10 to the 11th meters. Then we plug it into the same equation we used before, where the speed equals the square root of 6.67 times 10 to the negative 11th times 2.00 times 10 to the 30th over 3.00 times 10 to the 11th. This comes out to about 70,000 meters per second, or 7.00 times 10 to the 4th meters per second. Assuming the same period, we conclude that if you increase the radius, the speed will also increase. This concludes our presentation.
Shout out to Tommy Sabatino.